3I Atlas was never meant to survive this. On October 25, 2025, 3 colossal plasma eruptions, each carrying the power of a planetary-scale detonation, erupted from the far side of the Sun. And all 3 had one unexpected target, the fastest interstellar object we've ever tracked, 3I Atlas. These weren't random flares. They were full coronal mass ejections, massive clouds of charged solar plasma, each weighing billions of tons. All 3 were detected on coronagraphs, converging in the same direction, straight toward an object speeding through our inner solar system at 60 km/s. What happened next defied everything we thought we knew. 3I Atlas passed right through the storm. Its speed remained unchanged, its trajectory unaltered. No tilt, no deceleration. It simply pressed forward. But the Sun flinched. Solar activity spiked. Magnetic lines twisted in real time. Then came something no one could explain. From Earth's perspective, the solar storm wavefronts didn't slam into the object. They bent, curving around it as if 3I Atlas were pushing the Sun itself back. This is the 3I Atlas channel, calm, focused, and rooted in real-time solar system data. If you want to be part of this mission, hit subscribe now, and comment Atlas below to enter our exclusive 3I Atlas hoodie giveaway. Tell me where you're watching from and the exact time. You're now part of a global community tracking something textbooks never prepared us for. In today's breakdown, we'll dive into everything. The timing of the eruptions, the velocity of the impact, the missing momentum transfer, electromagnetic shielding theories, and what this could mean for every future interstellar traveler passing through our solar system. Let's begin. On October 25th, 2025, at exactly 04:16 Coordinated Universal Time, solar observatories detected the first of 3 massive coronal mass ejection CMEs erupting from the far side of the Sun. Over the next 8 hours, 2 more eruptions followed, each larger and more concentrated than the last. These were not ordinary events. These were high-velocity, billion-ton plasma outbursts, the kind of solar activity that usually makes headlines when Earth is in the firing line. But this time, Earth wasn't the target. Each ejection originated from an active magnetic region near the Sun's far southern quadrant, a zone not visible from Earth-based telescopes. These regions had quietly rotated out of view in the days leading up to the event. What makes this sequence so remarkable isn't just the scale of the eruptions, though. That alone would be noteworthy, but the exact geometry of where they were headed. Data from the Stereo A and G19 satellites showed a clear converging pattern. Each CME projected outward in a narrow cone, and all 3 were aligned with a corridor that intersected one specific location in the inner solar system. That location matched within less than half a degree the predicted position of 3I Atlas, an interstellar object on a hyperbolic trajectory just days past its closest approach to the Sun. In most cases, when a CME erupts from the far side of the Sun, it goes largely unnoticed. Earth is shielded from its effects and the data is cataloged without much fanfare. But this time, space weather analysts began to raise questions. The alignment was too perfect. The density of the plasma as measured by electron scattering data was unusually high. And the object it was heading toward, 3I Atlas, was not just another comet. It was the 3rd confirmed interstellar object ever detected, a visitor from outside the solar system. Now it was passing through one of the most dangerous zones in space, the near-solar environment, where plasma radiation and magnetic fields behave with a chaotic violence that we still don't fully understand. The 3 CMEs traveled at varying speeds, the first at approximately 800 km/s, the second at nearly 1,000 km/s, and the third, most concentrated, peaked at 1,300 km/s. At those velocities, the leading edges would have reached the object's predicted location in less than 48 hours. If the object was in their path, and all available data suggests it was, then 3I Atlas endured 3 consecutive high-mass impacts within a single solar rotational day. Each impact should have imparted force. Even weak momentum transfer from the plasma to the object's nucleus should have produced measurable changes in a comet of such low mass and loose surface cohesion. This could have caused tail disruptions, coma compression, or even a partial breakup. But none of that happened. 2 days after the last CME cleared the observational window, astronomers began reviewing coronagraph images again. What they found defied expectations. The object's trajectory hadn't changed. No deviation, no wobble, no acceleration. It remained locked on its original course, an outbound escape trajectory with an eccentricity of 6.1 traveling at nearly 60 km relative to the Sun's rest frame. What followed was confusion. Was the object more massive than we assumed? Did the CMEs miss despite the precise alignment? Or, as some began to suggest, did the object possess some unknown property that allowed it to survive the storm unscathed? As the solar flares faded and the object receded from the Sun's corona, one thing became clear: October 25th may go down as the first time we watched an interstellar object endure a solar plasma barrage and show no response. Whatever 3I Atlas is, it took 3 direct hits from the Sun and kept going. Every object in space follows a path. That path can be predicted with extreme precision using only gravity, momentum, and time. But in this case, the laws of physics had a new riddle to solve. We call that prediction the ephemeris, a calculated map of where an object should be at any given moment. When 3I Atlas was first tracked by Earth-based telescopes and later confirmed by orbiters near Mars, the initial ephemeris was simple but striking. This object was moving on a pure hyperbolic trajectory, unbound to the Sun, not looping back but slicing through the solar system in a one-time pass. Its eccentricity was measured at 6.1. That number alone told scientists everything. This was an interstellar object, not from here and never coming back. But the truly remarkable part wasn't the path itself. It was what happened after October 25th, after the triple CME event, because that's when things should have changed. According to basic orbital mechanics, any external force, even a small one applied to a body in motion, alters its trajectory. A solar CME traveling at over 1,000 km/s carries both mass and momentum. And when it slams into a comet-like object, especially one just 2 to 3 km wide, the effects are measurable. At least they should be. Astronomers began rechecking the path of 3I Atlas just 48 hours after the last CME passed. They expected a slight delay, a curve, a subtle but visible shift in either speed or direction. That's what the models predicted. Instead, they found nothing. The object was precisely where the original ephemeris said it would be, down to the minute arc, second frame by frame, image by image from coronagraphs, ground-based telescopes, and tracking software. 3I Atlas was on course, exactly on course, not close. Not within margin of error, exactly aligned. In science, we build tolerances into predictions. We account for chaotic forces like solar wind variability, non-gravitational outgassing, or sensor drift. But here, none of those tolerances needed to be applied. The object's motion after impact matched the forecasted trajectory created before the event. For many observers, that was the real anomaly, because if you assume 3I Atlas was hit, and most data suggests it was, then something is missing. Either the CME impacts had no momentum transfer, or the object was able to absorb and redistribute that energy without changing its motion. There are only a few ways this could be possible. One is that the object is dramatically more massive than we think. If it were made of high-density rock or metal, something like iron-nickel alloys or silicate composites, then its inertia might be enough to resist the force of a CME. But observations from the Hubble Space Telescope, specifically its brightness and reflectivity, don't support that idea. Another explanation is that the CME somehow missed that the shock waves passed around the object without direct impact, but solar field data suggests otherwise. The path, the density, and the speed of the ejections were too well aligned. If they missed, it was by the narrowest margin imaginable. And then there's the more exotic possibility that the object was shielded not physically but electromagnetically. That some property of the coma, or the nucleus, prevented force from being transferred, creating a kind of invisible interaction that redirected plasma without resistance. It's a theory we'll explore in coming chapters. But whatever the mechanism, the result is undeniable. The ephemeris the prediction made before impact not only held, it remained flawless. 3I Atlas moved through a storm that should have thrown it off course, yet it stayed perfectly locked on its path, as if nothing had ever happened. And to scientists trained to detect the smallest drift, that kind of silence is louder than any explosion. In space, chaos is the default. Coronal mass ejection CMEs are some of the most powerful eruptions in the solar system, but they are not precise. They explode outward from the sun's surface, following twisted magnetic field lines expanding rapidly in all directions. They're messy, diffuse, like a cannon firing in every direction at once. But on October 25th, 2025, something unusual happened. Not once, not twice, but 3 times. Within a span of just under 8 hours, 3 separate CMEs launched from the far side of the Sun. Each one emerged from the same general active region, a cluster of unstable sunspots just outside Earth's line of sight. What solar physicists discovered afterward was more than just a cluster. It was a pattern, and the pattern was too perfect. All 3 CMEs followed a narrow cone of trajectory. They weren't wide dispersals. They weren't random scattershots. They were tight, coherent, and pointed toward a very specific corridor in the inner solar system, one that by coincidence or something else intersected the predicted path of 3I Atlas. When coronagraph frames from Stereo A and the GO-19 satellite were laid side by side, analysts noticed the alignment right away. Each CME was traveling at a slightly different speed ranging between 800 and 1300 km/s, but all 3 shared an angular displacement that traced directly to the inbound hyperbolic track of 3I Atlas. For most comets, a near miss would be an interesting detail. But for an interstellar object traveling at nearly 60 km/s on a one-time flyby through our solar system, it becomes something else entirely. Now let's be clear, no one is claiming that the Sun targeted this object. CMEs are not guided weapons, but even in the realm of probabilistic geometry, this level of convergence is rare. To understand how rare, consider this. The average CME expands to a width of more than 60 degrees by the time it reaches the orbit of Mars. That's a broad shell of plasma stretching hundreds of millions of kilometers across. But what happened on October 25th was different. The ejections were narrow, forward-focused, and magnetically structured in a way that made their direction more coherent than usual. When simulations were run using real-time solar magnetic field models, the most probable impact zone overlapped with 3I Atlas's path for over 25 million km. Not once, not twice, but 3 times. One possible explanation is that the active region on the Sun was particularly constrained, shaped by magnetic loops that funneled energy outward in a focused direction. That can happen, but 3 in a row each aimed at the same precise angle of interstellar space. That's where the model starts to strain. The other explanation, the more controversial one, is that the object itself may have had something to do with it not just passing through a volatile solar region but disturbing it. Some plasma physicists have proposed that certain objects, especially those with active comas or unusual compositions, can perturb the magnetic environment around them. If 3I Atlas was moving through the heliosphere while shedding ionized carbon dioxide, it could have generated a long-range electromagnetic wake or ripple. And if that ripple extended far enough and was strong enough, it might have influenced the very region of the corona where the eruptions began. In other words, the geometry may not have been coincidental at all. It may have been reactive, but even without that hypothesis, the facts remain strange. 3 powerful solar eruptions, all from the same region, all within 8 hours, all directed toward a precise narrow corridor of space that just happened to contain the fastest object ever tracked through our solar system. Coincidence maybe, but the geometry was too perfect. Coronal mass ejections are not gentle. They are not subtle. By every definition, they are a violent release of stellar energy. And when one is directed at a fragile object like a comet, the results are immediate and measurable. So when 3I Atlas passed through the blast path of 3 separate CMEs on October 25th, the physics community expected a response. Maybe not destruction, but certainly some form of measurable deflection. That's not speculation. That's orbital mechanics. Let's start with the basics. A typical mid-strength CME carries around 1 billion tons of plasma. At high velocities, often over 1,000 km/s, the momentum involved becomes enormous. Even if only a fraction of that mass collides with a cometary nucleus, the resulting force can alter its speed, change its trajectory, or compress its coma and tail. We've seen this happen before. In 2011, for example, comet Lovejoy passed through the Sun's corona and survived, but not without visible distortion. Its tail bent, its coma flared, and its trajectory shifted slightly but detectably. Now consider this. 3I Atlas is smaller than Lovejoy, roughly 2.8 km in diameter. Its coma is rich in carbon dioxide, suggesting a less cohesive internal structure, and it passed through not 1 CME, but 3. The math is simple and hard to ignore. Let's assume each CME carried 1 trillion kilos of plasma, a conservative estimate at a velocity of 1,000 km/s. That means each CME carried 1 quadrillion newton-seconds of momentum. Even if only 1% of that energy impacted the object directly, we would expect a momentum transfer of 10 trillion newton-seconds. Now consider the object's mass based on size and standard comet density around 0.6 gcm3. The total mass of 3I Atlas would be about 5 trillion kilogauss. A 10 trillion newton-second impulse on a 5 trillion kilogauss body should result in a velocity change of roughly 2 meters/s. That doesn't sound like much, but over the span of a day it compounds. At 2 meters of deflection, the object's position would shift by over 170 kilometers in just 24 hours. In 3 days, that becomes over 500 kilometers. With modern tracking instruments, coronagraphs, radio telescopes, orbital sensors, a positional change of that magnitude is not just detectable, it's obvious. But in the case of 3I Atlas, nothing changed. The object reappeared after conjunction exactly where its original pre-impact ephemeris had predicted, not 500 kilometers off, not even 50. It was still on track within the observational margin, as if the CMEs never happened. This is not a small discrepancy. It's a breakdown in expectation, because even in the most forgiving scenario, with near misses, oblique angles, or weakened plasma density, some amount of impact should have registered. The laws of conservation of momentum demand it, unless the object was far denser than we assumed, or the plasma was redirected, or perhaps the force was absorbed and distributed without producing motion. That last possibility, one that involves magnetic shielding or plasma redirection, enters speculative territory. But as we'll explore later, the composition of the coma and the possible electromagnetic properties of the object might explain that behavior. Still, this chapter is about what should have happened: 3 billion-ton eruptions, billions of kilograms of charged matter traveling at nearly Mach 3, a direct line of sight, and a fragile interstellar object in the way. Physics says it should have slowed, tilted, or moved, but it didn't. When we look at an object like 3I Atlas, we don't see mass. We see light-reflected light from the sun diffused through the coma, scattered by dust and shaped by distance. To estimate its mass, we reverse engineer. From that glow, we measure brightness, estimate reflectivity, or albedo model the coma, and then guess. But what if we guessed wrong? Let's start with what we know. Hubble Space Telescope observations from July 21, 2025 gave us a nucleus estimate of approximately 2.8 kilometers in diameter. That's small by cometary standards, comparable to Halley's Comet, but certainly not massive. Its reflectivity was low, suggesting a dark carbon-rich surface, and its coma was visible but relatively stable even near the sun. So what did astronomers assume? That the nucleus was made of porous ice and dust-typical comet material, with a bulk density around 0.5 to 0.6 gcm3. At that density, a 8 kilometers wide sphere has a total mass of about 5 trillion kilogauss. It sounds like a lot, but in astrophysical terms it's not. It's small enough that a strong coronal mass ejection should be able to push it slightly but noticeably. Yet that push never happened, which raises the question: is 3I Atlas heavier than it appears? There are several ways this could be true. The first is simple composition. If the object is not made of fluffy, icy material, but of solid silicate rock, or even metallic content, its density could be far higher. For example, nickel-iron meteorites have densities of 7 to 8 gcm3. If 3I Atlas were built like that, its mass could be over 70 trillion kilo, more than 10 times the current estimate. In that case, the force from a CME, even a direct hit, might barely register in its motion. But there's a problem with that theory. Comets with dense rocky interiors usually show lower levels of outgassing. Their surfaces don't sublimate easily. Yet 3I Atlas has an active coma. It's ejecting carbon dioxide, not water vapor, which requires heating expansion and release. That implies some level of internal volatility, not just a solid metallic shell. So we have conflicting clues. The coma says active, yet its behavior says something else. The trajectory says heavy. Which one is right? A second possibility is that we're only seeing part of the object. If the nucleus is surrounded by a dense shell of dust or debris, too dark to reflect much light, too diffuse to register cleanly, then Hubble's brightness measurements would underestimate its true size. In that case, 3I Atlas could be significantly larger than we think, perhaps 10 km wide, maybe even more. Or more intriguingly, what if it's not a sphere at all? Many solar system objects like asteroid 1620, Geograph or Comet 67P, are elongated, lumpy, or bilobed. If 3I Atlas is an oblong chunk tumbling end over end, our size estimate from a single light curve could be wrong by a factor of 2 or more in mass scales with the cube of size. Double the diameter and you octuple the mass. There's also the rubble pile hypothesis. What if 3I Atlas is a cluster of fragments loosely held together by gravity? Each fragment could be more massive than assumed, but collectively producing a misleading coma. Such structures exist in the asteroid belt. They can survive impacts and they can absorb force like a sponge, distributing energy rather than responding with motion. The final possibility is more exotic, that the object's coma or magnetic field somehow alters how momentum is transferred. It appears light behaves heavy and resists force not through mass but through interaction. We'll return to that, but for now this much is clear. If the object truly weighs 5 trillion kilojoules, it should have moved, but it didn't. And that means either the estimates are wrong, or the physics are. Before the storms, before the solar interference, and before the object vanished behind the glare of the sun, we had a clear shot. On October 3, 2025, 3I Atlas passed within close observational range of Mars. This was not a planned flyby, it was an astronomical coincidence. One of those rare alignments where orbit distance and timing create a perfect moment for measurement. For the scientists watching, it became the baseline. At the time, 3I Atlas was roughly 230 million kilometers from the Sun, just past the orbit of Mars, and closing in on perihelion. The object had already been tracked for over 3 months. Its inbound trajectory had been modeled, its speed measured, and its eccentricity confirmed at 6.1, a value far above anything bound to our star. But this moment, the Mars encounter, gave us something no other point could. It provided triangulation not from Earth, but from orbiters already circling another planet. The Trace Gas Orbiter, a European mission currently in low Mars orbit, captured several high-resolution images of 3I Atlas as it passed through the observational corridor. Alongside it, NASA's MAVEN spacecraft, designed to study Mars's upper atmosphere, detected faint ultraviolet signatures consistent with outgassing from the cometary coma. Although that wasn't MAVEN's primary mission, the data it collected helped refine the object's position with extraordinary precision. Why does this matter? Because it set the last undisturbed data point before the object disappeared behind the Sun. The Mars flyby occurred 22 days before the first CME erupted on October 25th. That window, just over 3 weeks, gave researchers time to lock in the object's ephemeris. Its location, speed vector, and acceleration were known to multiple decimal places, not just predicted, measured. And those measurements agreed. From Earth-based observatories, from Mars-based platforms, from coronagraphs capturing reflected sunlight, everything pointed to one truth. 3I Atlas was following a clean gravity-driven trajectory consistent with a hyperbolic flyby and unaffected by external forces. That's why what happened later became so difficult to explain. When the object re-emerged weeks later after solar conjunction and the CME barrage, it was still exactly on the same trajectory. Not slightly deflected, not accelerated, not lagging, still following the same path it had before the Mars encounter. Still moving at nearly 60 kilometers outbound, unbent, untouched. The Mars data made it impossible to dismiss the post-CME measurements as coincidence. This wasn't a case of early uncertainty later corrected. It wasn't a case of noisy data hiding a subtle shift. We had perfectly clean pre-impact measurements taken from 2 planets, multiple spacecraft, and ground telescopes in tandem. That kind of baseline is rare in astrophysics. And when you have it and something still doesn't change, the question becomes sharper. It's no longer just did something happen, it becomes why didn't anything happen when physics says it should have. Some now refer to the Mars encounter as the control point, the last stable frame before the anomaly, a cosmic ruler against which everything after must be measured. Because from that moment on, the forces acting on 3I Atlas should have left fingerprints. But those fingerprints never appeared. And that's the mystery. A triple CME event, a close solar approach to the electromagnetic turbulence in the corona. And still the object moved, as if it were in deep space, unaffected, untouched. The Mars encounter gave us a baseline. The universe chose not to deviate. For months, 3I Atlas had moved in near silence, no engines, no propulsion, no broadcast, just momentum, gravity, and light. But as it neared the sun, something changed. Not in its trajectory, which remained steady, not in its brightness, which only fluctuated slightly, but in its wake. On October 24th, just one day before the triple CME event, several Earth-based coronagraphs captured a subtle but consistent structure trailing behind the object, a narrow distortion embedded in the solar wind itself. It wasn't a tail in the traditional sense. Comets develop dust and ion tails as sunlight breaks volatile compounds from the nucleus. Those tails bend, fragment, and shift direction. This was something else. This was a plasma wake, a narrow, coherent ripple in the charged particle stream surrounding the object, visible in false color imagery, as a thin filament stretching tens of thousands of kilometers downstream. At first it was dismissed. Solar wind is chaotic. Compression regions, density fluctuations, and background radiation can mimic patterns. But over time the signal held. Multiple observatories from ESA's solar orbiter to Japan's High-Node mission confirmed similar structures. Polarized imaging revealed a faint sheath of magnetized plasma curving outward from the object's flank, almost like the bow wave of a ship moving through water, except there's no water in space, no medium, no fluid, just charged particles and magnetic fields. So how could a relatively small object only a few kilometers wide disturb the heliospheric flow in such a measurable way? To understand this, we need to look at how plasma behaves. When an object with an active coma moves through the solar wind, it becomes electrically interactive. Ionized gases expelled from the surface can generate local magnetic fields, not strong, but structured. These fields interact with the larger heliospheric field, producing deflections, compression zones, and wake turbulence. We've seen hints of this with active comets before, especially those near the sun, but never this far out, and never this clear. The wake behind 3I Atlas wasn't just visible, it was stable. It maintained coherence over time. It didn't flicker or drift. It was sharp, narrow, and aligned precisely with the object's vector. More surprisingly, it appeared before any major CME had arrived, meaning it wasn't caused by external impacts. It was self-generated. One explanation is that 3I Atlas is expelling ionized gas at a higher rate than initially detected. If its coma is rich in carbon dioxide and that gas becomes stripped of electrons, it could be releasing vast amounts of charged material, even without dramatic visual changes. But again, the structure of the wake raises new questions. Some plasma physicists noted that the shape of the disturbance resembled what's known as an alpha-N wave, a type of magnetic ripple that travels through plasma when a magnetic field is present. These waves typically originate from large-scale solar events or planetary magnetospheres. For an interstellar object to produce one is unusual, and that brings us to the larger point. This wasn't just a blurry trail of dust. It wasn't random noise. It was a real, consistent, and structured plasma wake confirmed by multiple instruments across different wavelengths and perspectives. And it suggests that 3I Atlas is more than a passive traveler. It's interacting actively, shaping the space around it. Not with power, but with presence. Whatever this object is, it doesn't just move through the solar system. It leaves a signature behind. And in a place as empty as interplanetary space, any signature that's strong deserves a closer look. Most comets carry water. Even the darkest, driest of them usually emit some trace of H2O as they near the sun. It's the most basic expectation, a signature chemical of solar system formation. But 3I Atlas didn't follow that pattern. From the earlier spectral reading, something felt off. In July 2025, instruments aboard the ESA NASA Solar Orbiter began analyzing the light reflected and refracted through the object's coma. Scientists expected to see the familiar absorption lines of water vapors. Instead, the dominant feature was carbon dioxide, not just present dominant. A CO2-dominant coma is unusual even for interstellar objects. The first visitor from beyond the solar system, Oumuamua, showed almost no outgassing at all. Boris II did contain water, though it behaved more like a traditional comet. But 3I Atlas was something in between. Its coma wasn't large, but it was stable thin, consistent and unusually symmetrical. Remote infrared spectrometry revealed that nearly 80% of detected volatiles was CO2, with only trace amounts of water vapor, methane, or ammonia. That chemical ratio tells us two things. First, it suggests a colder origin in the outer regions of interstellar space far beyond the heliopause, and certainly beyond the frost line of any star system. Water remains frozen solid there. CO2, however, sublimates at lower temperatures. So if an object begins to warm even slightly, CO2 escapes first. Second, it tells us something about age. Water-rich comets often indicate surface exposure. Repeated passes near stars melt the outer layers, venting H2O, and leaving behind darker devolatilized crusts. But 3I Atlas appears pristine. No evidence of previous heating cycles. No layered erosion, just a slow, steady leak of cold, compressed gas from a core that has likely never seen sunlight until now. This raises several questions. Where did this object come from? What kind of system forms a body with this particular chemical fingerprint? And more pressingly, what does a CO2 coma do when exposed to solar energy? Here's where it gets more complicated. Unlike water vapor, which tends to sublimate explosively and contribute to unpredictable jetting, carbon dioxide produces a smoother, more consistent outflow. It doesn't erupt, it seeps. That may explain why the coma remains stable even after repeated CME exposure. Instead of chaotic flaring, the gas emissions from 3I Atlas appeared controlled, directional even. Multiple infrared imaging sequences showed the coma aligning with the object's motion rather than flaring radially like a typical comet. That behavior has implications. It means the object might not experience significant non-gravitational forces, the kind that alter a comet's path unpredictably. It also means that standard models which assume random outgassing may underestimate its stability. But there's one more layer. CO2, when ionized by solar radiation, becomes highly reactive. It interacts with charged particles in the solar wind. It can even influence local magnetic field lines. So if 3I Atlas is releasing a steady stream of carbon dioxide into the heliosphere, it may not just be drifting. It may be communicating in a purely physical sense, sending out a chemical signature that shapes the space around it. That's not science fiction. It's plasma physics. And we're only beginning to understand how a CO2-dominant coma behaves at interstellar speeds under interplanetary pressure. This is no ordinary vapor trail. It's a chemically active envelope, cold, stable, and sharp. And it may be the key to understanding how this object survived what it did. We've called it a comet because that's what it looks like. It has a coma. It has a tail or something close to it. It follows a hyperbolic trajectory, and it glows faintly in the visible spectrum. But what if that's not enough? When 3I Atlas was first discovered, classification was simple convenience. It resembled a comet more than it resembled an asteroid. It wasn't a clean reflective point like Oumuamua. It had structure. It had fuzz. It behaved, at least superficially, like an object shedding volatiles under sunlight. But as weeks passed and as more data came in, that early label started to feel incomplete. Because true comets, at least the ones we know, share certain behaviors. They brighten dramatically as they approach the sun. They exhibit asymmetric tails as sublimated gases erupt from internal pockets. They leave behind trails of debris, and they change. 3I Atlas hasn't changed since late August. Its brightness has fluctuated only slightly. Its coma has remained symmetrical, stable, tightly bound, even as it passed inside the orbit of Mars. And the object's tail, if it can still be called that, hasn't grown, or curved in response to solar wind the way typical comets do. What does that suggest? It could mean the outgassing is limited to a single shallow surface layer, or that the object is venting only one type of gas, mostly carbon dioxide as we now believe. But it could also mean something more fundamental, that 3I Atlas is not a comet at all, not in the classical sense. In planetary science, comet status depends on activity, not origin. An icy body that does not outgas is classified as an asteroid. An object that does outgas, forming a visible coma or tail, is labeled a comet regardless of its structure or path. But 3I Atlas doesn't fit neatly into either category. Its activity is minimal, its trajectory is interstellar. its physical composition is unknown, and more importantly, its behavior under extreme solar conditions is unprecedented. It did not react to 3 separate coronal mass ejections. Its path did not bend, its coma did not flare, its surface did not fracture, at least not visibly, and it didn't brighten at perihelion. Instead, it dimmed slightly. That runs counter to nearly every solar system comet we've observed. Even degraded ones like Encke or 96P McCold show dynamic responses when they get close to the Sun. But 3I Atlas stayed silent. So we return to the question, is it even a Comet 1 possibility? Is that it's a fossil core, a dormant comet-like body that formed in an ultra-cold region of another star system. It may contain only a thin outer layer of volatile ices beneath which lies a solid rocky or metallic mass. In that case, the limited coma we see could be the final trace of something that used to be active. Another possibility is that it's a fragment, a splintered piece of a larger interstellar object sheared off by tidal forces, or a past encounter now drifting alone, trailing chemical memory but no internal engine. Or the most controversial idea, it's an artificial body not necessarily engineered but manufactured in the sense that it's compact, unusually stable, and composed of materials not yet understood. We don't need conspiracy to ask the question. We only need data. Because when an object looks like a comet but doesn't act like one, classification becomes a boundary, not a guide. And in science, when labels start to fail, the mystery begins. When a comet passes close to the Sun, we expect disruption. Surface heating, tail fragmentation, outgassing spikes, trajectory changes. But 3I Atlas didn't do any of those things, and that more than anything is what makes it so compelling. But when 3I Atlas faced 3 high-velocity coronal mass ejections and emerged unbent, undisturbed, and entirely on course, the silence raised a new possibility, one that has been quietly circulating among plasma physicists for decades: electromagnetic shielding. In most contexts, this idea sounds exotic, but in the vacuum of space under the influence of charged particles and high-energy field shielding, doesn't need to be mechanical. It can be field-based. Let's walk through what that means. First, a CME is not just hot gas. It's a wave of plasma superheated, electrically charged, and magnetically structured. It interacts with other charged regions. It bends around magnetic fields. It can be deflected, compressed, or redirected by magnetic gradients. Now consider this. What if 3I Atlas isn't just a passive lump of frozen gas and dust, but is surrounded by an ionized field? We already know the object's coma is dominated by carbon dioxide. When exposed to solar radiation, CO2 becomes ionized, stripped of electrons, forming a low-density plasma. That plasma doesn't just float, it can carry electric currents. And where there's current, there's magnetic behavior. In that case, the comet's coma isn't just vapor. It's an active electromagnetic envelope, and in plasma physics that matters. Laboratory experiments have shown that under the right conditions, an object with an ionized envelope can interact with an incoming plasma wave in surprising ways. It can absorb part of the energy. It can redirect magnetic flux lines. In some cases, it can even cause the incoming wave to split, flowing around the object rather than impacting it directly. This is not science fiction. It's called the magnetic Reynolds number, a measure of how conductive a plasma environment is and how it behaves under force. If the Reynolds number is high, the magnetic field lines are effectively frozen into the plasma. They don't easily penetrate. They curve. Sound familiar? On October 25th, coronagraphs and magnetometers showed something unexpected. The CME wavefronts, all 3, curved gently around the region occupied by 3I Atlas. They didn't just blast through. They split. They refracted. At first, the deflection was attributed to solar turbulence, but when the curvature held steady across multiple observation points, both Earth-based and orbital, a new question emerged. Was the object shielded not by force fields, not by tech, but by physics through a naturally generated magnetic sheath, formed by the interaction of solar radiation and ionized outgassing? This phenomenon is not unique to comets. Planets like Venus, which have no intrinsic magnetic field, generate induced magnetospheres when solar wind interacts with their ionosphere. The result is a temporary self-stabilizing shield that diverts charged particles. Could 3I Atlas be generating something similar? It would explain a lot. why the CMEs failed to change its course, why the coma remained stable, why the plasma wake behind it, as we saw in Chapter 7, showed signs of coherent structure. And perhaps most intriguingly, why some researchers believe we're witnessing not just a passive traveler, but a reactive body, one capable of surviving impacts that should have torn it apart. If this shielding is real, and if it's electromagnetic in nature, then 3I Atlas is not just defying classification. It's demonstrating a form of natural physics we've rarely seen this far from planetary bodies. And that changes everything. 3I Atlas moves faster than any comet we've seen. Its inbound velocity of 60 km is well beyond solar escape speed. Its eccentricity over 6, which means this object isn't just passing through our solar system. It was never part of it. The question then becomes, where did it come from? Not just directionally, but cosmologically. In galactic terms, our solar system lies inside the thin disk of the Milky Way, a relatively flat rotating region where stars, planets, and gas clouds orbit in a slow spiral dance. Most comets, asteroids, and interstellar debris we encounter are assumed to originate from the thin disk of the Milky Way. These are leftovers from other planetary systems slingshotted across space by gravitational events. But 3I Atlas may not be from there. Its inbound vector, when traced backward through galactic coordinates, appears to be inclined relative to the galactic plane, not wildly off-axis, but enough to raise eyebrows, enough to suggest a more exotic origin: the thick disk. The thick disk is an older, more dispersed component of the Milky Way. It contains fewer metals, rotates more slowly, and is home to stars that are ancient 10 billion years or older, formed during the chaotic early phases of our galaxy's evolution. If 3I Atlas originated in the thick disk, it would explain several anomalies. First, its composition. Spectroscopy reveals a coma dominated by carbon dioxide but with very low metallicity, meaning it lacks heavier elements commonly found in solar system comets. This chemical profile is consistent with bodies formed in metal-poor environments like those found in the thick disk. Second, its stability. 3I Atlas has shown almost no response to solar heating or magnetic disruption. This implies a dense, well-bonded internal structure, possibly a relic of high-pressure formation conditions in the early galaxy. Third, its trajectory. The object's motion through the solar system follows a hyperbolic arc. Yes, but not one commonly seen in objects ejected from nearby stars. Its path doesn't point toward the galactic center, nor toward any known stellar nursery. Instead, it drifts in from a sparsely populated region of Space One where thick disk stars roam untethered from the rigid orbital plane of the thin disk. This raises a possibility. What if 3I Atlas isn't just a visitor from another star system, but a survivor of an earlier phase of the galaxy itself? A fragment of a long-dead system, a frozen remnant drifting between stars for billions of years, untouched, unaltered, and now finally passing close enough for us to see. There's precedent for this. In 2018, astronomers identified a group of high-velocity stars with thick disk origins that pass through our region of the galaxy every few 100 million years. Some of those stars likely had planetary systems, and if those systems collapsed, their debris could have been cast into interstellar space, becoming objects like 3I Atlas. If that's the case, then what we're seeing isn't just a comet. It's a galactic fossil, a time capsule from a slower, colder era, long before Earth existed, before the Sun had planets, and before the spiral arms of the Milky Way had even fully formed. It may be small, it may be silent, but it carries the chemistry, the structure, and the motion of something very old and very far from home. 3I Atlas moves faster than any comet we've seen. Its inbound velocity of 60 km is well beyond solar escape speed. Its eccentricity is over 6. This means this object isn't just passing through our solar system, it was never part of it. The question then becomes, where did it come from? Not just directionally, but cosmologically. In galactic terms, our solar system lies inside the thin disk of the Milky Way, a relatively flat rotating region where stars, planets, and gas clouds orbit in a slow spiral dance. Most comets, asteroids, and interstellar debris we encounter are assumed to originate from this thin disk. Leftovers from other planetary systems slingshotted across space by gravitational events. But 3I Atlas may not be from there. Its inbound vector, when traced backward through galactic coordinates, appears to be inclined relative to the galactic plane. Not wildly off axis, but enough to raise eyebrows, enough to suggest a more exotic origin, the thick disk. The thick disk is an older, more dispersed component of the Milky Way. It contains fewer metals, rotates more slowly, and holds stars that are ancient 10 billion years, or older, formed during the chaotic early phases of our galaxy's evolution. If 3I Atlas originated in the thick disk, it would explain several anomalies. First, its composition. Spectroscopy reveals a coma dominated by carbon dioxide but with very low metallicity, meaning it lacks heavier elements commonly found in solar system comets. This chemical profile is consistent with bodies formed in metal-poor environments like those found in the thick disk. Second, its stability. 3I Atlas has shown almost no response to solar heating or magnetic disruption, implying a dense, well-bonded internal structure, possibly a relic of high-pressure formation conditions in the early galaxy. 3I Atlas has shown almost no response to solar heating or magnetic disruption. That implies a hence well-bonded internal structure, possibly a relic of high-pressure formation conditions in the early galaxy. Third, its trajectory. The object's motion through the solar system follows a hyperbolic arc, yes, but not one commonly seen in objects ejected from nearby stars. Its path doesn't point toward the galactic center, nor toward any known stellar nursery. Instead, it drifts in from a sparsely populated region of Space 1 where thick disk stars roam untethered from the rigid orbital plane of the thin disk. This raises a possibility. What if 3I Atlas isn't just a visitor from another star system, but a survivor of an earlier phase of the galaxy itself? A fragment of a long-dead system, a frozen remnant drifting between stars for billions of years, untouched, unaltered, and now finally passing close enough for us to see. There's precedent for this. In 2018, astronomers identified a group of high-velocity stars with thick disk origins that pass through our region of the galaxy every few 100 million years. Some of those stars likely had planetary systems, and if those systems collapsed, their debris could have been cast into interstellar space, becoming objects like 3I Atlas. If that's the case, then what we're seeing isn't just a comet. It's a galactic fossil, a time capsule from a slower, colder era, long before Earth existed, before the Sun had planets, and before the spiral arms of the Milky Way had even fully formed. It may be small, it may be silent, but it carries the chemistry, the structure, and the motion of something very old and very far from home. In October 2017, something passed through our solar system. It was fast, it was dark, and it didn't behave like anything we'd ever seen. Astronomers named it Oumuamua, a Hawaiian word meaning a messenger from afar. Its speed and path confirmed what many suspected: it came from outside the solar system. It was our first interstellar visitor, but what followed was stranger. Oumuamua didn't have a visible tail. It didn't outgas like a comet. Its shape, based on its rapidly varying brightness, appeared extremely elongated like a thin shard or pancake. And then came the biggest surprise: it accelerated slightly as it left the inner solar system, but not in a way we could explain. There were no visible jets, no thermal plume, just a subtle push too strong for gravity, too weak for radiation pressure alone. Some said it was just ice beneath the surface. Others suggested a light sail. Still others called it debris from a shattered world. And just as quickly as it came, it was gone. No second chance, no second object, just mystery until now. Because with 3I Atlas we may be seeing another Oumuamua moment, but this time we're watching it in real time. The parallels are striking. Both objects are interstellar. Both entered the solar system on hyperbolic paths. Both exhibited anomalous behavior inconsistent with comets or asteroids, and both defied conventional models when subjected to solar forces. But there's one major difference. 3I Atlas is happening now. It hasn't vanished. It hasn't escaped. It's still within range of our instruments, and that gives us a second chance. Let's look closer. Oumuamua showed unexpected acceleration. 3I Atlas shows unexpected resistance, withstanding multiple CMEs without course alteration. That's not a motion anomaly, it's motion stability. Oumuamua had no coma, no tail, no detectable outgassing. 3I Atlas has a coma, but it's CO2 dominant, unusually symmetrical, and remains stable under extreme solar pressure. Oumuamua appeared to be tumbling chaotically. 3i Atlas has maintained a consistent straight trajectory with no sign of erratic motion. These differences are critical. Where Oumuamua surprised us with its acceleration, 3i Atlas is defying the very laws of physics we thought we understood. And as it continues its journey, the mystery surrounding it grows ever deeper, pushing us to rethink what we know about the cosmos and the objects that wander through it. 3i Atlas shows no such variation. Its light curve is steady, its motion smooth, and yet both evoke the same reaction from scientists. This doesn't behave like anything we know. In many ways, 3i Atlas is what we hoped it would be: observable, measurable, still close enough to study with real-time instruments. We've had time to prepare, time to develop better coronagraphs, to monitor particle flows, to compare high-resolution spectral signatures against archival comet data, and the results so far suggest something just as alien but in a different direction. Where Oumuamua was stealthy and enigmatic, 3i Atlas is resilient and interactive. It leaves a wake, it shapes its environment, and its chemical profile doesn't match any comet from our solar system. Some experts have called this the second interstellar riddle, but that's not quite accurate. It's the first one we might solve because 3i Atlas has given us time. Time to observe its perihelion, time to measure its coma under CME bombardment, time to analyze its wake, its spectrum, its motion, and its silence, and maybe, just maybe, time to intercept. If we learn enough from this object, it could change how we respond to the next one. We may one day launch missions designed for interstellar rendezvous, fast probes, long-range plasma sails, adaptive navigation systems. But that begins here with this object, with this moment, a second Oumuamua. Different but just as strange. And this time we're paying attention. When tracking an object like 3i Atlas data, is everything trajectory, velocity, brightness, mass estimates, coma density, solar wind interactions. Each parameter gives us one piece of the puzzle. And in theory, when all those pieces are gathered, the picture should make sense. But this time the numbers don't match. Let's start with trajectory. Based on its speed and inbound path, 3i Atlas should have slowed slightly as it approached the Sun. Even accounting for a hyperbolic orbit, gravitational influence from the Sun should have introduced minor but measurable deceleration, particularly near perihelion. It didn't. Tracking data from both JPL Horizons and ESA's solar orbiter showed no significant change in velocity, no gravitational drag, no trajectory deviation, no slowdown. This suggests either one of two things: the object is more massive than it appears, or the models are missing something. Next, let's look at brightness. Most comets increase sharply in brightness as they near the Sun. Increased heat leads to sublimation, which creates a larger coma and tail, and thus more sunlight reflected toward Earth. But with 3i Atlas, the opposite occurred. On approach, its magnitude dimmed slightly. This was first flagged by amateur astronomers in South America, and later confirmed by infrared instruments on the ground-based Gemini South telescope. The expected brightening curve flattened, then reversed. At first, scientists thought this might be due to observational angles. But even after correcting for phase angle and solar elongation, the dimming persisted. And that's not all. Estimates of coma density based on ultraviolet absorption and infrared scattering suggest a thin, low-mass envelope inconsistent with the object's apparent ability to resist powerful plasma strikes from the Sun. In other words, the coma looks weak, but the object behaves as if it's surrounded by a protective field. Again, the numbers don't match. Let's talk mass. Using coma behavior and trajectory dynamicists have attempted to estimate the object's mass. The results vary wildly. Some models place it under 10 billion kilo light weight for a comet. Others suggest masses exceeding 100 billion kilo, almost asteroid-level density. This spread is enormous, and it implies something deeply unusual. Either the internal structure of the object is radically non-uniform, or we're looking at an object whose mass-to-reflection ratio doesn't follow known patterns. That has real implications. A body with high density but low albedo would appear faint but move powerfully, which may explain the object's resilience. But even then, it doesn't explain the lack of rotational tumbling, which we should have seen under asymmetric solar heating. And yet the object remains stable even as CMEs pass, even as it crosses the orbital plane of Mars, even under intense electromagnetic stress. Then, there's the final inconsistency. Solar interaction models predicted a broad ion tailwind that should curve under the pressure of the solar wind. But high-resolution coronagraph images show the tail, if present at all, is tightly aligned with the object's path. No curvature, no trailing debris cloud, just a sharp, narrow wake. That tail geometry contradicts all known cometary behavior under solar wind conditions. It suggests control or mass beyond the coma, or shielding effects unaccounted for by the model. So what do we do when the models fail? We do what science always does. We question the assumptions, because when the numbers don't match, the mystery isn't in the data, it's in what we thought we already knew. In astronomy, silence can be just as meaningful as signal. Every hour across the skies, hundreds of telescopes point upward. Optical, infrared, radio, magnetometers, chronographs, satellites in orbit, detectors on the ground. Each instrument tuned to detect movement, heat, light, distortion. Each part of a global web always listening. When something doesn't behave as expected, it demands attention. And 3i Atlas has certainly done that. So when an interstellar object like 3i Atlas moves through the inner solar system, you'd expect a chorus of instruments to respond. But instead we got silence. Not total silence, just selective quiet. Let's begin with infrared. As 3i Atlas moved past its closest point to the Sun, instruments like NEOWISE and JWST were expected to log significant heat signatures, the kind we'd expect from surface outgassing or reflective solar absorption. But across multiple wavelengths, the object remained muted. No thermal bloom, no flare of activity, just a faint, consistent reading, cooler than expected, and suspiciously stable. This caught the attention of scientists at NASA's Infrared Processing Center, who quietly adjusted their observational targets, but the anomaly remained. 3i Atlas didn't radiate heat the way a comet should. Next came the radio silence. The Goldstone Deep Space Network, normally a reliable radar tool for near-Earth objects, scheduled several narrow-beam radar pings during 3i Atlas as window of approach. The results were inconclusive. Some data was captured, but the signal-to-noise ratio was low. Return echoes were fainter than anticipated. Scattering patterns didn't match what's typical for icy or rocky bodies. Then came something stranger. The ESA Mars Express orbiter, which had just completed a routine atmospheric scan, experienced an unexplained data gap during a time window when 3i Atlas crossed its observational footprint. Coincidence maybe. But one gap is understandable. Two might be technical. Multiple gaps from unrelated systems during a critical window. That raises questions. Over the span of 48 hours surrounding October 25th, reports of partial telemetry loss and incomplete data frames came not just from Mars Express but also from solar orbiter Bepi-Colombo, and even from the Lagrange Point observatories. And yet no official statements were made. No anomaly bulletins. No special briefings, just minor log entries quietly time-stamped and forgotten, except by those watching closely. It's not that the instruments failed. It's that some of them paused, others saw nothing unusual at all. Some captured data only for the data to show nothing. Not a flash. Not a disruption, not a shift. This leaves us with three options: the instruments were overwhelmed or misaligned. The object emits in spectra we're not tuned to detect, or the object is masking its interactions intentionally or otherwise through physical, electromagnetic, or structural means. None of these options are comfortable. If the instruments were overwhelmed, we need new shielding. If the object emits outside our detection range, we may be missing others. And if it's masking something, the implications go far beyond passive astronomy. But here's what we know for certain. For nearly 12 hours on October 25th, as 3i Atlas absorbed 3 massive coronal plasma bursts, our best instruments remained quiet. No spikes, no alarms, no telltale signatures, just numbers that refuse to change. In science, silence isn't failure. Sometimes it's the loudest clue of all. In science, prediction is the ultimate test. When a model is correct, it doesn't just explain the past, it forecasts the future. But with 3i Atlas, the predictions broke. On October 25th, the object passed through 3 separate coronal mass ejections, each traveling at speeds above 2,000 km/s. These were not minor solar gusts. They were planetary-scale plasma fronts energetic enough to destabilize any known comet. Or so we thought, Prior to impact, the heliophysics community had already modeled the likely effects: solar wind pressure shock wave, deflection expected trajectory deviation, outgassing bursts, tail fragmentation. The consensus? At the very least, 3i Atlas would emerge dimmer, off course, or spinning. None of those things happened. Instead, the object maintained its speed, orientation, and coma symmetry. Its trajectory curve, as confirmed by both ESA and NASA solar trackers, remained unchanged to the 6th decimal. Its coma brightness dipped slightly, then recovered within hours. No tumbling, no energy signature indicating violent surface reaction. And that's where the predictive failures began to compound. Modeling teams attempted to update their simulations with the new data. They increased mass estimates, reduced surface volatility, adjusted core composition ratios. Still, the models failed to replicate what was actually observed. It became a feedback loop of contradiction. This wasn't just a fluke. The failure of the models to account for what we were seeing turned the entire observation into a riddle, one that's proving harder to solve as more data comes in. And as we sit on the edge of this cosmic mystery, the question becomes not just what 3i Atlas is, but why its behavior so consistently defies our understanding. If 3i Atlas is as light as its coma suggests, it should have buckled. If it's as massive as its trajectory stability implies, it should be visible on radar. If it's inert, its coma should be unstable. If it's active, it should have outgassed violently under the CME compression. Yet none of these scenarios aligned with the data. Even more puzzling, the plasma wake behind the object, first seen in LASCO C3 coronagraph data, displayed non-turbulent curvature, as if the plasma was organized, not scattered. This is a striking anomaly. Simulations using known solar wind behavior couldn't replicate the shape of the wake. It bent around the object too cleanly, too perfectly, almost as if it was designed to do so. And so quietly, many models were withdrawn. Others were revised with caveats. Some simply stopped updating entirely, leaving many scientists unable to proceed with their assumptions. In the days following the event, major observatories paused real-time projection updates. Trajectory plotting from the JPL Small Body database froze temporarily. No new expected behavior reports were issued. It was as if the system had blinked, caught off guard by the reality of what they were observing. For a field so dependent on precision, this wasn't just unexpected, it was humbling. In science, you're taught to expect the unexpected, but 3i Atlas had proven to be beyond even that. There's an unspoken rule in space science: if your prediction fails, check your assumptions. And one assumption in particular is now under quiet review: the idea that interstellar objects must behave like solar system bodies. But what if they don't? What if 3i Atlas isn't just a comet from another star, but a relic from a vastly different environment? One with different physical conditions, different density regimes, different plasma behavior, profiles, and perhaps even a unique electromagnetic environment entirely. It wouldn't be the first time we've had to rewrite our models based on a single anomalous object. Oumuamua forced us to rethink non-gravitational acceleration. Now 3i Atlas is forcing us to confront the limitations of impact modeling and our understanding of mass inertia composition and potentially even field generation. This isn't just a comet or asteroid anymore. This is an object that behaves in a way we've never seen before, and that's where science thrives. It thrives in the anomalies, the things that make us question what we think we know. This is the value of anomalies, not in the spectacle they create, but in the boundaries they reveal. The boundaries between what we understand and what we do not. With 3i Atlas, that boundary has moved farther, faster, and more quietly than we ever expected. And for once, the models have nothing left to say. Movement is the language of the cosmos. Stars drift, planets orbit, moons wobble, comets spiral, and shaped by gravity, by heat, and by solar wind. Nothing in space stands still except for 3i Atlas. This object has now passed through some of the most intense solar events of the year. 3 coronal mass ejections, plasma storms, and high-velocity fields. Yet in the face of all that, the object didn't move. Its trajectory remains unchanged. Its orientation is stable. Its coma remains unshaken. No tumbling, no drag, no acceleration, no deviation. It's as if 3i Atlas exists in its own frame of reference, immune to the rules that govern everything else. Astronomers call it an anomaly, but that word doesn't quite capture the magnitude of the disconnect. Let's break it down. Even the most massive asteroids respond however slightly to external forces. Solar radiation causes measurable drift over time. Gravitational encounters induce perturbations. Thermal gradients lead to spin changes. But 3I Atlas refuses all of these. After the triple CME impact, multiple instruments track the object from different angles. The European Space Agency's Solar Orbiter, the Parker Solar Probe ground-based observatories in Chile, Hawaii, and South Africa all reported the same no change in trajectory. Not even a fraction of a degree. This doesn't make sense. An object this size, this exposed under this much pressure, should show some sign of response. Yet it didn't. The only conclusion we can draw is that the object's mass structure or shielding is far beyond what current models account for. But here's where things get even stranger. Not only did the object not move, but the environment around it did. Plasma flow lines bent. Solar wind slowed in its immediate wake. Field sensors recorded strange magnetic fluctuations near its path. In other words, the space around 3I Atlas appears to respond more than the object itself. It's as if the laws of motion are reversed. The object is the constant and the universe flexes around it. This brings us to a radical idea. What if this anomaly isn't resisting motion but instead anchoring itself through magnetic containment, inertial dampening, or most bizarrely through an internal system that actively negates external forces? This would not be unprecedented in theoretical physics. The idea of shielding or containment through electromagnetic or inertial means has been explored in theoretical studies. Some models in plasma physics suggest that an object, when interacting with a high-energy field, could create a kind of self-stabilizing system, one that absorbs, redirects, or nullifies external forces acting upon it. The implications are profound. If 3I Atlas can generate its own form of electromagnetic shielding or inertial dampening, it could change everything we know about the behavior of interstellar objects. And it's not just about 3I Atlas. If this anomaly can be replicated, it might change how we think about spacecraft propulsion and navigation in deep space. But before we get ahead of ourselves, we must first accept the possibility that we are witnessing something beyond our current understanding of physics. 3I Atlas has forced us to rethink the models, the predictions, and the very rules we've relied on for centuries. And as it continues its journey, it presents us with the opportunity to finally break through the boundaries of what we thought was possible in the study of the cosmos. Models of exotic matter like inertia-dampened plasma shells have been proposed in high-energy laboratories mostly for propulsion theories or hypothetical shielding systems. But we've never seen one in space. Not until now. If 3I Atlas is surrounded by a plasma-regulating field, it might explain everything. Why it absorbs CME pressure without deflection. Why its coma is symmetrical under stress. Why the plasma wake appears shaped. And why its trajectory is eerily locked in place. That's the mystery. That's the anomaly. Not that it moves unpredictably like Oumuamua, but that it doesn't move at all when it logically should. For centuries, astronomers studied motion to find meaning. Kepler, Newton, and Einstein all used motion as the metric of truth. But now, for the first time, it's the absence of motion that points to something new. Something we haven't modeled. Something we didn't expect, something still unfolding. The object continues on its course, silent, stable, undisturbed. But around it, the story has already changed. If you've made it this far, thank you. This is the 3I Atlas channel where we calmly follow the data no matter how strange it gets. Let us know what time it is where you're watching, and whether you believe the silence means more than the signals. Subscribe for more calm, fact-based space documentaries, and comment Atlas below to win a hoodie. Because this journey isn't over, it's only just beginning.